down first, A horizontal. His moment arm, he is 5 feet away. So the moment arm is 5 feet. Now let me see which way he's going to roll. I drag him back here until he gets to this point right here. I tie a string to him. His arrowhead's pointing to the left. Were he to get away from me, he would roll this way. So that is a positive tendency to roll. So I put a plus in front of him. Now then I have two equations and two unknowns, and you just got to bang them out simultaneously. If you solve those two simultaneously, you'll find that this number comes out 18 kips, and this number comes out 5 kips, are the magnitudes of those two forces. Now from then on you can find the tension in any part of the cable, and you can find how far this drops down. For example, here is the piece AB. On this end of AB is somebody magnitude 5. On this end is somebody magnitude 18. Then this has to be this squared plus this squared, take a square root. That's the magnitude of AB. 5 squared plus 18 squared, and take a square root. Now to find out how far point B moves down, let's just put point B on here. We'll show the 6 kips. We'll show this arrow here. The force in that arrow is BC. We don't know its magnitude. We don't even know its direction because we don't know how far this next point is in the air. Up on this end we have 5 kips, and here we have 18 kips. We do know that this distance across here is 20 feet. And therefore you can sum moments about this point. The reason I sum moments about that point is because I don't know this guy here. Summing moments about point B will get rid of BC, and the equation reads an 18 kip load times his moment arm, Y for B, let's call it, how far B is below the reference axis, Y sub B. His tendency to roll about point B is that way. That's a plus. There's a 5 kip load. I know his moment arm, 20 feet. Were he to get away from me, he'll roll this way. That's a positive. The sum of all those moments is 0. I should have really written that down. Sum moments about B equals 0 is this, and I can solve for how far that point ducked down. Then I simply do the same thing from then on. It went down how far?
5.56.
5.56 feet. All you got to do then is just keep on from there. You say this one went down 5.56. You now know the magnitude of this force. You can solve for that one. You can sum forces horizontal. You can sum forces vertical. This is your 6 kip force. Here is your, we didn't solve for that. What was 5 squared plus 18 squared?
$18.7.
That was 18.7 kips. We now know that this force is sitting at an angle 5.55 by 20. Rather than calculating the angle, there's 5.55 drop and 20 horizontal. And here's BC. Now BC, you won't know the angle and you won't know the force, but that's two unknowns, and so you can solve for them. When you sum forces horizontal equals 0, you'll get one equation. When you sum forces vertical, you'll get another equation. Both of them will have BC and theta in it. You can solve for both of them. And the solution is in your notes there. We just stuck them in there. All right. Now then, let's say you have a bar, and that bar is supported by a pin at C and is supported at A by a rope. We'll discuss more about pins and rollers and stuff like that later, but I think most of you probably remember that pins can produce, they have the ability to produce two forces. That would be C horizontal and C vertical. Those are both unknown. On this free body of this bar, there is also a force in the rope. His name probably would be tension AB. The bar itself has some weight, and due to the symmetry of the bar, the centroid of the bar has to be at the middle, and therefore you could put its weight at the center of the bar. Now, I don't know what that bar weighs, but let's just say it's a 300 Newton bar. And let's just say R was equal to 10 meters. I'm not sure we need the distance there. Yeah, I guess so. Alright. Then that means that this distance is 10, and the horizontal distance is, since this is symmetric, that would be 45 degrees up here and 45 degrees in here, and therefore this would be 10 cosine of 45 degrees. How far is that?
7.1.
7.07 meters. Okay. Now then, all you got to do to solve for the tension force in the rope is sum moments about point C equals 0 equals. Sum moments about point C. I selected point C to sum moments about because two unknowns come through that point, and that makes it a good place to sum moments about. Those two will drop out. Is equal to the tension force in member AB multiplied times his moment arm. That's a 10 meter moment arm. His tendency to roll about point C, were he to get away from me, would be this direction. That's a negative tendency to roll. Then we have plus a 300 Newton weight, and I say plus because were it to get away from me, it's going to go this way. As close as he ever gets to point C is 7.07 meters, and I solve for tension force in a rope. You could then sum forces vertical and sum forces horizontal and get C horizontal and C vertical. Now this problem asked how long a bar do we need to stick out here in order to make this whole thing balance. It said that the bar was of uniform dimensions, means this isn't a piece of wood and this is a piece of lead. If it was, we would be okay. We would just have to get the weight of this piece of wood in terms of its length and the weight of lead. But in this case, they were all the same. And this whole thing is in the plane of the paper. Well, here is the centroid of bar piece BC. Here is the centroid of bar piece BA. Here is the centroid of bar piece CD. This moment arm right here is 100 millimeters, and this moment right here is L over 2. So to make that thing balance about point C, you would simply say, if it balances, then the sum of the moments about C is 0 is equal to. First off, there's 200 millimeters worth of stick times where his centroid is 100 millimeters Were he to get away from you, he would roll this way. Next, there is a, I got to know how long that little stick there is. It's 200 squared plus 150 squared. Take a square root.
250.
It's a 250 long stick. So then I would have a 250 millimeter long stick multiplied times, he has the same 100 length. And were he to get away from it, he also would pull the bar that way. That's a plus tendency. This one balances it in the minus direction. Minus L multiplied times his moment arm is L over 2. And you saw for how long the bar needs to be to make the whole thing hang horizontally as shown at C. Now that's really finding the finding the centroid of a piece of wire. In other words, if somebody wanted to know where you could balance this piece of wire on a knife edge, in other words, where is its centroid, that's how you could do it right there, find its centroid. All right. Centroids of plane areas, they use about the same idea. First, in order to find the centroid of a strange looking piece like this would be to break it up into pieces that don't look so strange. Break it up into a solid rectangle that you totally understand how big it is and where his centroid is, and divide it up into a rectangle whose centroid you know where that is. And of course the centroid of a rectangle is in the middle, halfway. And then the equation says y bar is area 1's area times how high his own personal centroid is, plus area 2's area times how high his centroid is above some reference axis. You should always pick the base as the reference axis. It makes the numbers come out easier. Divided by A1 plus A2. So for our case, that comes out equal to, let's call the top one area 1, let's call the bottom one area 2. Area 1 is a 50 millimeter by 300 millimeter, and his distance of the centroid is to the middle of the piece. That's 250 plus half of 50 is 275 millimeters. Now that's also just about like if you cut this out of a piece of cardboard and cut the whole thing out of a piece of cardboard and put it on a knife edge right here. It's obviously going to fall off the knife edge. How hard this one wants to fall off is his weight or his area times how far up he is. So that's what we're calculating. We're calculating how much tendency to roll about the reference axis does this little piece of cardboard have. Then there's some more. Area 2. Area 2 is 50 millimeters wide. It is 250 millimeters deep, and its own personal centroid is halfway up this 250 dimension, which is 125. Then you divide by the sum of the areas, which is already written down, so that's no problem, plus 50 times 250. Be careful every now and then, and one of the answers on the quiz probably will be, I see students cancel the 50, cancel the 300, cancel the 50, cancel the 250. That's called fast math. It's not right. Equals to, and before you tell me that, let me tell you that you ought to be able to balance a piece of cardboard as shown right about here. And by right about here I mean, and I'm not sure, I think I like it a little higher than that, right about here. And that to me looks like about 200 millimeters. So you ought to get a reasonable guess as to what it ought to be. In other words, if you get 280 millimeters, there's no way that you could balance that piece of cardboard cut in the shape of a T about a line on a knife edge right through here. What'd you get?
206.8.
206.8 millimeters. So probably the answer in the book might be 210, something like that. The centroid location horizontally is found by the same exact method. In this case, due to symmetry, this would be a waste of time. You would draw a reference axis at the base. You would then mark it up into areas or divide it up into areas you understood. You would multiply each area times his own personal height plus this next area times his own personal height, and then divide by the sum of the two areas. But due to symmetry, the centroid is guaranteed to be down this axis. Alright, the next one works the same way. It is an I-beam that somebody has put a cover plate on top of it. Your job would be to divide this up into area 1 that you understand. You could omit these little radiuses. Area 2, which you understand fully. Area 3. Let me put the centroid for area 1. It's in the middle of the plate. Here's the centroid for area 2. It's in the middle of the plate. Here's the centroid for the middle of area 3. It's in the middle of the plate. Probably not on that x-axis there. And here is area 4. There would be area 4, and here would be its centroid. Now he has asked you to solve for how far down it is, so it makes sense to put the reference on that end of things. Either put it at the bottom or put it at the top. Call it a reference axis. Apply this equation. Y bar is equal to, and that's in your notes, that's in your reference manual. If it wasn't in your reference manual, you wouldn't care about it because they probably wouldn't ask you to memorize that equation. And solve for Y bar. Here's one where we have a couple of channels and a plate. In this case, the channel is 20 inches deep. We know where the centroid is. The plate is 18 by 1.5 inches. We know where the centroid is. If we call that area 1, we call this one area 2, and here's just another area 2, which we probably ought to be able to put in there, same numbers. Draw a reference axis at the base and apply the same equation. You would have to be told the area of these shapes. This area, of course, is 18 by 1.5 inches. Then you get how far up the centroid is by the same equation. And this is relatively important, so there's a couple of examples like this. This one has a channel on top of a wide flange. The dimensions of the channel were given, and the dimensions of the wide flange were given. And it's nothing more than an A1D1 plus A2D2 divided by A1 plus A2. Here's area 1. Here's D1 or Y1. Here's area 2. Here's Y2 divided by area 1 plus area 2. Tells you the location of the centroid. Now, the book gives you, excuse me, the reference manual gives you a product of inertia. I know you probably can't read that. Well, yeah, let's zoom down on that. Maybe we have a better chance. It's right up here. A little more. T. T. A little more, 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 a little more. That's good. Okay. And if you have to find one of these on the exam, then what you really do is you take the area, you take a little chunk, dA, you find out how far that is from the y-axis and how far it is from the x-axis. You find the x and the y position, multiply it times dA, and you integrate it. And that's generally no fun, and I'm not sure they'd give you one of those. but they tell you how, so it bothers me that they might ask something simple. So this is important. When one or both of the x or y axes are axes of symmetry, then the product is 0. What this term really measures is how far it is out of balance about both axes. So a circle, it's 0. A triangle, it's not symmetric, but it is symmetric, and therefore I sub xy is 0. A wide flange is symmetric and symmetric, so it's 0. Piece of pipe, symmetric, so I sub xy is 0. That's, unless you're going to learn how to do this, and you probably don't have time unless you already know this. If you have even one axis of symmetry for the thing they're asking you about, the right answer is no I sub xy. Alright. And might as well leave it there. Alright. Now then, we're going to do some friction. Friction is the phenomena that when you try and slide something across the floor, it doesn't want to go, and you push on it a little harder and it doesn't want to go, and you push on it a little harder and it pops loose, and then it starts to move. There are actually two coefficients of friction for most things. One is a coefficient of friction static, and one is a coefficient of friction kinetic or dynamic. The static coefficient of friction is generally larger, might be 0.2. If that's the case, then once you get it moving, this is the coefficient of friction it takes to break it loose. Once you get it moving, the little raised spots and indentations and imperfections that used to be kind of locked together are pretty much dynamically rattling across each other, and so this number drops maybe to this. So if somebody asks you how hard will it be to break the box loose, that's the number you're looking for. If he asks you, will the box break loose, see what that does to you. See how much force it takes to break it loose, and if you got more than that, then the answer is yes, the box is going to move. Now this problem asks what value of P would be necessary to keep the crate from falling backwards and killing the guy, and also how big would P have to be to push it up the plane. Let's first answer the question, how hard would it be? How hard must you push to keep the thing from sliding down? As you might imagine, if this was a ice sheet with a 0 coefficient of friction, then probably the thing would just fall right down. You'd have to push on it pretty good. Now, these problems require that you draw a free body. Here's a free body of this crate. Gravity is pulling straight down on it. This particular crate doesn't tell us the weight, so probably we would just call it W. Because the crate is sitting on the plane, there will be a resisting force, usually called the normal force. That angle between these two is 20 degrees. And since you have told me the crate is going to fall down, friction always resists movement. So if you want to know what's going to happen when the crate falls down, you must show me the friction force pointing up. Now you may be used to seeing that the friction force is equal to the coefficient of friction times the normal force. And that's kind of true, but what it really is the friction force is always less than or equal to that. It may get that big, and it can't get any bigger, but the truth is it could get smaller. In other words, if this number right here comes out 80, it may be the friction force is only 40, is all that's needed. In our case, since we're talking about it actually just getting ready to slip and fall down, we would be able to replace this with an equal sign, but be careful with that. Now that free body is kind of hard to see. This free body is really easy to see. So rotate your quiz 20 degrees, and then you can write all your equations. Some forces in the normal direction, we'll make this the in direction, and we'll call this the y direction actually, and call this the x direction. Sum of the forces in the y direction has to be 0, is equal to, first you have a force in, then you have a weight acting down, except not all the weight is acting down, only the weight times the cosine of 20 is acting down. And then here's this P force. Now the P force used to be horizontal, but when I rolled my quiz 20 degrees, the P force rolled up 20 degrees, and that P force has a downward component and a horizontal component. And the downward component, that's 70 degrees in there, would be P cosine 70, and it acts down, so minus P cosine 70 degrees. That gives me one equation. This is not considered an unknown. In other words, the box has some weight to it, and the boss is going to have to tell me, or it might cancel out of the equations for all I know. Now secondly, the sum of the forces in the x direction has to equal to 0. Is equal to, the normal force doesn't have any x component, so I don't have to fool with that, minus the friction force, but that friction force is coefficient of friction times normal. That's as big as it ever gets, and I want it to get that big. In other words, when this thing is just ready to slip, this will start off at 10 pounds, 20 pounds, 30 pounds, 40 pounds, 80 pounds, 200 pounds, and finally get up to this number, and then this number will get no larger. So I put the biggest number in here, to the left minus, plus W times, if that's 20, this is 70, so W cosine of 70 degrees. The P force now acts, minus P times the cosine of 20 degrees. I know the coefficient of friction, I know the weight, I know all these cosines of angles, and I have two equations and two unknowns. I can solve for both of them. I can solve for the normal force is equal to something, and I can solve for the P force is equal to something, and this is of course the one I'm looking for. Now, in order to find the magnitude of the P force necessary to make the block go up the hill, all I do is note that the guy is pushing, it didn't move. Push a little harder, please. It didn't move either. Push a little harder, please. All of a sudden it breaks loose. The minute it breaks to the left, this friction force changes now and goes to the right. So every equation where the friction force was a plus number, now the friction number is a minus number, or vice versa. That friction number only showed up in one place. That's right here. So only change would be right there. And then you would solve for P again. You'd know for or how much it would take to get the crate moving up the hill. Another friction problem. Refrigerator. He wants to know, will it slip or will it tip once you put a P force required to move it? And the coefficient of friction is 0.4. So first, we'll put the weight of the refrigerator on there, 200 pounds. This one's nice and square with the world already. That's kind of nice. No doubt this normal force is 200 pounds. There will be a friction force. Since you're pushing to the right, the friction force will go the other way, always. And the friction force will be 0.4 of 200 pounds. Because you said you wanted to slide the refrigerator. 0.4 times 200 pounds. This one ought to be not much to this one. The force necessary to make it slide is 0.4 times 200 pounds. You're not going to get it going